Hello everyone, my name is Ahmed. I'm currently a student in Casablanca in Morocco. Me and my mentor Tim have been working very hard on this project, and I'm excited to show what we've come up with. So we'll be starting off with a quick introduction, explaining why I decided to pursue this project and the intent behind it. Then I'll explain you GPT's architecture, so how it works on a surface level. Then I'll explain the methodology, so all the math, theory related stuff. And finally, using our results, I'll come up with the conclusion and application. Hope you enjoy. I'm sure we all recognize these symbols. ChatGPT in the left, Google Bard in the middle, and Bing AI on the right. And whether we openly acknowledge it or not, they have become crucial for our daily lives, for the worse or the better. I mean, we become lazy writers, lazy programmers, and even continue to feed our needs for instant gratification. However, the question is, do the pros outweigh the cons, or do the cons outweigh the pros? Here we have a list of the notable pros and cons of using GPT. Some notable pros are that it's efficient and fast in communication, it can handle large data, and it's very versatile. So from ideation to writing to programming, even programming. However, one of the cons is that it provides inaccurate information. From my personal experience, you should never use ChatGPT as your personal Wikipedia, as it's very unreliable. Another con is that over-relying on ChatGPT can only lead to laziness. It can cause you to lose your writing skills and even programming skills. While all this is subjective, one thing is for sure, ChatGPT is unpredictable. So as NYU professor Sam Bowman says, because systems like this essentially teach themselves, it's difficult to explain precisely how they work or what they'll do. For example, when you write in a prompt in GPT, when you write in the same prompt in GPT, it always has something new to say. It always gives unique answers, and it does never repeat the same output. And basically, in other words, what NYU professor said is that ChatGPT is unpredictable, and even the top computer scientists around the world do not know exactly what they'll output and do not know precisely how they work. And this is why I'm here today. I'm here to take on this unique angle of AI. While a lot of research is focused on development, improvement of AI, not as much research is focused on safety, control, and ethics. I'll be doing this by exploring the human imitation of GPT generations. So, how does GPT work on a surface level? Generally, GPT takes n tokens in and outputs one token out. What are tokens? Tokens are chunks of text generated from a tokenizer algorithm. This tokenizer algorithm separates large text into smaller segments by certain rules. This can be spaces, punctuation marks, and special characters. So as we can see here, we have an input token, we need to, and it will predict an output token, cut. And then this output token cut will be incorporated with the next iteration of input token. Now, as you can see, cut is part of the input, and we have the input we need to cut. And then it will predict another output. Now it's carbon. Now it will continue incorporating the output token with the next iteration until a stopping condition is reached, indicating all generation is complete. However, it does not just simply take an input token and predict an output token, but rather it provides a statistical distribution of all possible tokens. This statistical distribution is created by training the AI model on large internet data. So this can be social media conversations, travel blogs, Wikipedia pages. So the AI model learns to make associations between words that commonly co-occur and analyze the statistical vocabulary characteristics in human text. As you can see, the choice of human text is very diverse. It goes from social media conversations to Wikipedia pages to help the AI model have a good grasp. This is why the neural networks are trained to provide high accurate probability distributions for the possible tokens, and high probability token is chosen from the distribution. So in general, GPT learns by making associations between words that commonly co-occur and cannot produce text without being prompted. Hence, it is not able to surpass humans, but it can only imitate their language. So the methodology. So we'll be looking at statistical vocabulary characteristics that GPT imitates, more specifically ZipF's law. So ZipF's law is this pattern that is found in large text data sets. Here, ZipF's law states that the the frequency of the elements at rank R is proportional to the rank of the elements. In other words, the most frequent word occurs twice as often as the second most frequent word, and 3 times as often as the third most frequent word, and 4 times as often as the fourth most frequent word. On the left, you can see the graphical representation of Zipf's law, and on the right, you can see the mathematical representation. So to help visualize things, we'll have an example here. So here, let's say the most frequent word in a data set has a frequency of 2,400. Based on Zipf's law, the second most frequent word should have a frequency of 2,400 over 2, 1,200. And the third most frequent word should have a frequency of 2,400 over 3, 800. And the fourth most frequent word should have a frequency of 2,400 over 4, 600. So this pattern is observed in a large data sets or any large text extracts. And this is why it's going to be useful in analyzing GPT text. So here I use 2 data sets for this research. I use a Shakespeare-Kaggle data set of different text extracts and plays from Shakespeare's text. So 2 rank frequency graphs were plotted for the 100 most frequent words, 1 excluding stop words, 1 including. So what are stop words? Stop words are words that add no meaning to the sentence. They're basically prepositions, pronouns, etc. And I had another data set, which was GPT-4 data set, which was self-made by asking GPT to generate Shakespearean style text. And again, 2 rank frequency graphs were plotted for the 100 most frequent words, 1 excluding stop words and 1 including. So we can see visually that the human Shakespeare graphs look a lot like Zipf's law. However, they do not resemble it perfectly. And the only reason why is because as you use a larger data sample. So we were talking about how the human Shakespeare data set imitated Zipf's law. As you can see, the graphs resemble Zipf's law graph that we saw earlier. And then now the Shakespearean style GPT text surprisingly also resembled the Zipf's law graphs. So as you can see, it also has a close resemblance where it follows the rank is proportional to the frequency of the rank. So we cannot be so sure of this assumption unless we have some empirical measure. This is why I use the JSD measure. The JSD measure is a series of formulas that can be used to compare 2 different distributions. So in this case, we're going to compare the Zipf's law graph to the human Shakespeare data sets, and the Zipf's law graph to the GPT-styled Shakespearean style GPT data sets. And it goes through this series of formulas, some complex maths, and it gives a JSD value. In essence, the JSD value is a value between 0 and 1. And the closer to 0 the JSD value is, the more the 2 distributions are similar. So in this case, we got, for the GPT graph, we got a JSD value of 0.00858 when compared to Zipf's law graph. As the JSD value was very small and very close to 0, we can confirm our assumption that GPT does imitate Zipf's law graph, Zipf's law. And when looking at the human value, when looking at the human JSD value, we got a value of 0.01585. Which was slightly higher than GPT. However, it's still really close to 0, which means also the human text was imitating Zipf's law. I decided to take an extra step with this project. I decided to also look at the commonality between vocabulary in the human Shakespeare's data sets 100 most frequent words and the GPT Shakespearean style data sets 100 most frequent words. I excluded stop words since stop words are very commonly used in sentence structures and there would already be a lot of similarity. So excluding stop words, it's really tests the base vocabulary used in each data set. And surprisingly, there was a 32% words in common between the top 100 words. This means the similarity extends beyond mere stop words, but rather shows that GPT adapts its style of writing based on the prompt. So when GPT was asked to input a Shakespearean style text, it outputted accordingly, which shared a lot of similar vocabulary with actual human Shakespeare text. This connection can be attributed to GPT's training on internet data, allowing it to draw upon relevant internet-derived language patterns when responding to prompts, including those related to Shakespearean writing. To confirm this assumption, I did the same exact thing with Dickens writing. And again, I got a similarity of 20%. You might be wondering why there's a short decrease. but it's likely attributable to the more distinct writing style that the Shakespeare has, and also the stronger imprint Shakespeare writing has. I'm pretty sure any English teacher can recognize Shakespearean writing off the bat, since it has a very strong imprint. And as GPT is trained on a lot of internet data, it's also learns to statistically know how the Shakespearean style is. So lastly, to test the adaptability of styles based on certain prompts, I plotted human Shakespeare's datasets 100 most frequent words against their frequencies in the GPT Shakespearean style datasets. So as you can see, in the x-axis, it contains 100 most frequent words in human Shakespeare datasets against their frequencies in the GPT datasets. And now the ZipF's log graphs completely disappeared. There's no relationship. It's a mix of peaks and troughs, meaning that GPT does not perfectly imitate styles based on prompts. So it does not follow the complete order that Shakespeare writing has. So what can we conclude? We can conclude that GPT follows ZipF's distribution, and that it adapts its style of writing based on prompts given, drawing from the internet training data. The findings only indicated some level of surface level similarity between the two datasets based on the commonality of vocabulary. However, it did not emulate the styles perfectly. Using this conclusion, I created a solution and an algorithm I created my own GPT detection methods. So the 3 steps are compress, expand, compare. So let's call text A the text we want to classify, whether AI or human written. So we compress text A using features like short summary, type of text, tone of text. So this is the style of text. This is like Shakespearean style, but this is the style of text of the text A. So it helps us understand what is this text A and what is this style. Then using these features, GPT is asked to output the text and a data set is made after the same prompt was inputted many times. So we expanded it back to a GPT outputted generations. Then we'll compare the GPT generations with text A based on paraphrasing, sentence structures, and word choice. So a higher similarity between the comparison means a higher chance that the generations that text A is AI generated. So I also wrote an algorithm, and also if you want to check it out, please feel free to let me know. My Python code can be found here in my GitHub. And my closing remarks is that I wouldn't definitely call this a 100% accurate solution for GPT detection methods, as AI is growing in an exponential rate. It's going to continue to evolve, and the effectiveness of this method will always decrease. And as AI continuously evolves, its danger grows with it. I want to show this quote from Elon Musk that says, AI can be more dangerous to humanity than nukes. To all the computer scientists listening to this presentation, whenever you're writing a research paper or in the lab or working on AI projects, carry on this quote with you. As you can never know, you might just be the next Oppenheimer. Thank you.
Well, thank you, Ahmed, for that presentation. And please stay on camera here. Any questions for Ahmed on his insightful presentation? So, so Vidor asked the question, how do we not know that GPT is using other people's rendition of Shakespeare, as that is probably more numerous in its training data set? People who imitate Shakespeare's writing likely write with a harsher Shakespearean tone. Shakespeare himself probably didn't write that differently, so GPT imitating Shakespeare might be GPT imitating people imitating Shakespeare.
You're not wrong, to be honest, since GPT is trained on internet data, random internet data. But even if it was like a harsher tone, it still like gives an overall overview of the style of Shakespeare, and that GPT was able to at least imitate the overall style of Shakespeare, and this was shown by the commonality in vocabulary.
Got it. Thank you for answering that, and thank you to Vidor for the question. Any further questions for Ahmed? All right, in the interest of time, we'll have to move on. So, okay, Ryan, actually, perhaps it's best. Ryan, do you want to come to the stage and ask the question yourself?
Right. Oh. So you talked a little about how like you talked about like some values that you use that measured like the similarities of the data sets, and you like showed like how it's similar to like Zipf's law. Like if like you also mentioned that like there's that value for the human generated data set and the GPT generated value set were both like very similarly low. Like how can like future AI detecting softwares like differentiate the two if they're so close together?
No, that wasn't like you do not differentiate based on the JSD measure. The test was to check whether GPT was imitating Zipf's law. So it's a law that is observed in large data sets, large text extracts of human language. It's common in NLP, and in our findings, the JSD measure showed that GPT does in fact imitate Zipf's law, and that due to the JSD measure value being closer to 0, which means the two distributions when GPT was compared to Zipf's law was close to 0, that means GPT did inherit Zipf's law, which is a common statistical vocabulary characteristic found in large text extracts. Thank you for your question.